Have you ever wondered why modern AI suddenly exploded in intelligence, speed, and capability seemingly overnight? Why tools that once struggled to string a sentence together now write code, pass exams, translate languages, and have conversations that feel almost human? What if I told you that almost all of that progress traces back to a single idea, an idea so revolutionary that it quietly rewrote the entire future of machine learning? Today, we're diving into the groundbreaking paper, Attention is All You Need, the moment the old world of RNNs and LSTMs collapsed, and the era of transformers, the models behind ChatGPT, Gemini, Claude, and nearly every modern AI system, began. And trust me, once you see how this works, once you feel the elegance of the idea, you'll understand why this paper didn't just change AI, it detonated it. Before we go deeper, make sure to smash that like button, subscribe if you haven't already, and ring the bell so you never miss a deep dive into the world-changing technologies shaping our future. Now let's unravel the model that replaced recurrence, defied all expectations, and conquered almost every sequence-to-sequence task on Earth. Prior to this paper, neural networks for translation and language modeling were dominated by recurrent architectures, RNNs, LSTMs, and GRUs. These systems processed sentences one word at a time, in order, from left to right. That meant slow training, limited parallelization, and a painful struggle to capture long-range dependencies. If a sentence required connecting the first word to the 15th, the signal had to pass through 14 time steps, each one an opportunity for errors to accumulate or gradients to vanish. Convolutional models sped things up, but still required stacking many layers just to allow distant words to interact. Then came the idea so simple it seemed almost impossible. What if a model didn't have to read words sequentially at all? What if it could look at every word at once? What if instead of remembering information through time steps, it simply attended to whatever it needed, wherever it was, instantly? That idea is self-attention, and it's the beating heart of the transformer. Here's how it works. Every word in a sentence, the, cat, sat, outside, gets converted into a vector, but instead of passing that vector through time, the model compares it against every other word in the sentence using queries, keys, and values. Think of a query as the question a word asks, the key as the identifier that determines whether another word is relevant, and the value as the information that should be shared. The model calculates attention scores by taking the dot product of the query with all keys, scales them by the square root of the dimension to keep gradients stable, and applies a softmax to turn them into probabilities. Then, it uses those probabilities to blend the values, producing context-rich representations that know exactly which words matter. And because these operations happen on entire matrices, they run in parallel. No recurrence. No marching word by word. Suddenly, training that used to take weeks could be done in hours. And that's just the scaled dot product attention mechanism. The transformer amplifies this idea with multi-head attention, projecting queries, keys, and values into multiple smaller subspaces. Each head can specialize. One head might track syntactic structure, another resolves verb relationships, another follows entities across sentences. After attention, the outputs are concatenated, projected again, and pass through position-wise feed-forward networks that expand and contract dimensionality to refine the representation. And because the model has no inherent sense of order, positional encodings, sine and cosine waves of different frequencies, are added to embedding so the model knows the difference between dog bites man and man bites dog. The entire transformer is built from stacks of these layers, 6 in the encoder, 6 in the decoder. The encoder processes the input sequence with self-attention, producing a rich representation of the entire sentence. The decoder, while also using self-attention, is masked so it cannot look ahead, preserving autoregressive generation. Then, critically, the decoder attends to the encoder's output, allowing it to translate or produce text based on everything the encoder understood. Residual connections and layer normalization stabilize training, dropout prevents overfitting, shared embeddings reduce parameters, and the model is optimized using Atom, with a warm-up learning rate schedule that ramps up and decays following the inverse square root of step number. The results? They weren't just good, they annihilated everything before them. On English to German translation, the transformer achieved state-of-the-art BLEU scores while training faster and costing dramatically less compute. The base model already crushed previous architectures, and the big model pushed performance even higher, establishing new records. English to French? Same story. The transformer didn't just win, it won while being simpler, faster, more parallelizable, and easier to scale. And here's the twist. The paper wasn't just about translation, it was a blueprint. Because the authors realized something profound. If attention can replace recurrence in translation, why not everywhere else? Why not use attention for speech? For images? For audio? For code? For everything? And that's exactly what happened. Within a few years, nearly every major AI breakthrough, from GPT to BERT to Stable Diffusion to AlphaFold, descended from this architecture. The transformer became the operating system of modern AI. But let's go deeper into why it works so well. First, self-attention provides constant path length between words. While RNNs have paths proportional to sequence length, self-attention connects all tokens directly in just a couple operations. That means long-range dependencies, like linking the beginning of a paragraph to its end, become trivial. Second, attention is massively parallelizable. GPUs thrive on large matrix multiplications, and the transformer leans into this, letting entire sequences be processed simultaneously. Third, multi-head attention lets the model capture multiple linguistic and semantic relationships at once, something recurrence struggled to do. Fourth, positional encodings preserve order without limiting the model's ability to generalize beyond training lengths. Fifth, because attention is decoupled from time, transformers scale. And scale is ultimately what produced the frontier models we interact with today. But this paper even dove into ablations, proving that every design choice mattered. Removing attention heads hurt performance, shrinking key dimensions hurt the model, increasing model size improved accuracy, dropout prevented overfitting, and positional encodings, whether sinusoidal or learned, were essential for stable training. The training strategy itself was also carefully designed. Using atom with beta 1 equals 0.9, beta 2 equals 0.98, and epsilon of 1e minus 9 kept optimization stable. The warm-up schedule allowed the model to gradually adapt before receiving higher learning rates. Label smoothing improved BLEU even though it worsened perplexity. And datasets like WMT 2014 English-German and English-French provided millions of sentence pairs to learn from. When you combine all these details, you get something deceptively simple, yet astonishingly powerful. A model that replaces recurrence with attention, convolution with attention, and complexity with clarity. That is why the transformer became the foundation of the AI revolution. It wasn't just a better model. It wasn't just a faster model. It was a new way of thinking, a new architecture that unlocked capabilities no previous system could dream of. And today, when you type a message into a chatbot, translate a paragraph, autocomplete code, or generate an image from text, you're using this paper's legacy. You're watching attention reshape the world. So if you want more deep dives into the breakthroughs that define our future, make sure you like the video, subscribe to the channel, and drop a comment letting me know which paper or technology you want me to explore next. Your support helps us keep creating these viral, high-impact explorations of the systems shaping humanity's next era. Thanks for watching, and I'll see you in the next one.